Hi class, welcome to our third and last video of notes for this chapter 15 on waves. In this video, we're going to talk about what happens when waves interact with another object, so hit another object or surface, or go around another object or surface. And we're also going to talk just a little bit more about light and sound waves specifically. So first, one way we can change our wave direction is when we undergo a reflection. This is when the waves actually hit a surface and bounce off. So if the surface is flat, then the angle at which the wave hits the surface is the same as the angle at which it leaves, meaning the angle in is the angle out. If we hit the surface at a 90-degree angle, straight on, then we're going to bounce out at a 90-degree angle. This is called, one too far. This is called the law of reflection. And again, it's just if we come in and hit a solid surface at an angle of 30 degrees, we're going to bounce off at an angle of 30 degrees in the other direction. The law of reflection. The next thing that can happen to change wave direction is refraction. Ooh, there we go. This is when the waves actually bend. So now when they're coming across a new surface or medium, they're going to bend. And this happens most specifically when waves enter a new medium. So for example, if we go from traveling through a gas, traveling through a liquid, like we are in this example of the pencil here, then the light as it's traveling through the gas is traveling faster. Once it hits the liquid, it slows down because we're in a new medium, and that's going to cause the wave to bend. So in this case, we're looking at the wave of visible light that allows us to see the pencil and the glass. And you can see the pencil looks like it's kind of broken or bent once it hits the surface of the water. And that's because the light that's traveling and allows us to see the pencil is also bending as it hits the surface of the water. Now, the amount that we're actually bending is going to depend on the medium that we're entering. So going from a gas to a liquid is going to cause a large bend. Going from a liquid to a solid could cause a large bend or even a complete reflection. The last type of way that we can change the wave direction is through diffraction. This is when we actually bend waves around an object. So the best way to think of this is to think about ocean waves bending around a rock. The amount of bending is going to depend on the size of the obstacle and the size of the wave. So if it's a really big obstacle but a small wave, you're going to get some bending around. If it's a really small obstacle and a really big wave, then there's not going to be as much bending. Large obstacles and small waves mean low diffraction or low bending. Small obstacles and large waves mean you're going to have a large bend. Again, the best way to picture this is ocean waves coming up and hitting against a rock or a boat in the ocean. You see those waves bend around that boat or bend around that rock. So again, just to recap real quick, reflection, we bounce off, so they hit and bounce back. Refraction, they're going to travel through, but they're going to bend as they travel through a new substance or medium. And then diffraction, we're going to bend around. So the three ways that we can change our wave direction is by bouncing off, traveling through, or bending and going around. Okay, our light waves. Light, as we've been talking about, travels in waves, specifically transverse waves. Those were those up and down looking waves. Light is a type of electromagnetic wave. That means that our light does not need a medium to travel through. Think about how light can travel through space. You see sunlight. You see light from the stars at night. In space, there's no air. There's no medium that light is traveling through, but it can still travel to our eyes. On Earth, that light is traveling through a medium. It is traveling through the air, the gas that's in the air. Our speed of light never changes. It always travels at 3 times 10 to the 8th meters per second. So the only thing that can change with our light is the frequency and thus the wavelength. And that's going to give us the different colors of light that we see and the different types of light. Now, when we talk light, a lot of times we just think the visible light that we can see. But visible light is just one tiny, tiny sliver of all of the light that there is. So this here is our electromagnetic spectrum. And what we're interested in right now is this back line. Our electromagnetic spectrum contains gamma rays, X-rays, ultraviolet, a little sliver here of visible light that you see kind of pulled out from that back line there, infrared waves, microwaves, and radio waves. As we travel from gamma rays, those have our shortest wavelength and the most energy, and they're traveling across towards our radio waves, which have the lowest energy and the lowest wavelength, lowest frequency. In the middle, we have, again, a tiny sliver right here down the middle of visible light. Visible light is our rainbow: violet, indigo, blue, green, yellow, orange, red. Usually, you see this the other direction as Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. That is the only part of the electromagnetic spectrum that we as humans can see. Other animals can see more into the ultraviolet, like some cats and dogs see more ultraviolet, and other animals might see more into the infrared area. But all of this is considered light. Even if we can't see gamma rays, they are light rays. They are waves of light that travel. So this is going to be important in knowing that the only part of the electromagnetic spectrum that we as humans can see is visible light, this tiny little sliver, but that there's other type of lights. If we talk gamma rays, X-rays, microwaves, radio waves, UV, or infrared, we're also talking about light. And everything on this scale that you're looking at right here travels at the same speed, 3 × 10⁸ meters per second. The only difference between violet light and red light is going to be the frequency and wavelength. The speed stays the same. Sound is our other most important type of wave in this chapter. It also travels in waves, but sound travels in longitudinal waves, those compression waves. And sound has to travel through a medium. We mentioned this in an earlier video in our notes. Usually the medium that sound travels through is air. So what happens when you speak, like I'm speaking now, your vocal cords vibrate and they're compressing the air around them. That compressed air is then moving out of your mouth through the room, and eventually those compressions and rarefactions are going to reach the ears of our listener, and then your brains are right now interpreting the compressions produced from the speaker as sound, and so you're able to hear what I'm saying. In the vacuum of space, there's no medium. There's no air or gases in space. It's just nothing. So there's no medium to transmit the sound waves. So in the emptiness of space, there is no sound. So if you were to be able to be floating in space and you took a hammer and you started banging that hammer against the side of the spaceship, there's no sound being made from that. Now here on Earth, if you were to take a hammer and bang it against something, you're going to hear that sound produced because there's air and a gas that those longitudinal waves can travel through. But again, in space, there's no sound. Now, we're able to hear in space because we connect through kind of an intercom system, walkie-talkies, but otherwise, without that air pumped into our helmet allowing us to hear, or the air pumped into the spaceship or space station allowing us to hear, there's no sound in the empty vastness of space. All right, that is it for your chapter notes. Please make sure that you have your note sheets fully filled in. Once you have those note sheets fully filled in, at this time you can work on your book notes for chapter 15. If you haven't yet finished those, you can also work on your Edpuzzle videos for chapter 15, which are posted on edpuzzle.com.